Hey, how's it going, everyone? Welcome to my stream. So, I was supposed to stream yesterday, but things didn't work out, so I'll be streaming tonight and probably tomorrow night. Tomorrow night would be the usual. I didn't get a lot of time since last stream to do a bunch of reading. I wanted to like read up on the VIA chip and start getting ready to implement that. I didn't have a ton of time to do that. In fact, I was super busy, so I just decided, I'm just gonna go ahead and kind of do that on stream. So it might be a little bit of, like maybe it won't be as exciting. Maybe I won't be typing in as much code and kind of reading and collecting information, but we'll see how it goes. In fact, I didn't even kind of finish what I had started at the end of last stream, which was I'd started working on this assertion macro, one that would effectively throw an exception under a certain condition, which would allow my debugger to catch that. I just want to kind of refresh my memory on what I did there. So yeah, I've got this like assert macro here. Oh yeah, and I remember last time I was doing this, which was really at the end of my stream, I had realized, let me just go to it. Yeah, I was looking at this, and then I was looking at the normal assert macro, like something like just here. Like the one from Visual Studio, for example, is a macro that looks kind of like this. And I was thinking I should totally do something similar. Like here you can see it does this cast to void to avoid any kind of warnings, and it basically does this not of the expression, which is another way of kind of doing, rather than doing like an if, you just say like not, this turns whatever expression here, whether it's a Boolean expression or not, turns it into a Boolean expression, and then they do a if that is true, we're done, or, and then they call their internal assertion function, passing in the stringized version of the expression and also the file and the line number. So I could totally kind of do the same thing, which I think is not a bad idea. Yeah. And I was thinking about how like I'm calling fail here. Rather than do that, I should really just have like my own like assert handler. And it'll be similar for now, but I think it'll be cleaner than having it be the fail handler. So okay, so let's just fix that up now, and we'll move on to the VIA after. Also, I'm a bit tired, so I'm not sure how long I'll be streaming tonight. We'll see how my brain works tonight. So okay, let's see. I've got assert here. I've got the condition. Yeah. So I'll just remove this do here and this while, and I'll do the not condition deal. Cast to void. Gonna remove some of this stuff here. Okay, let's do this. All right, void. No, that's not right. Okay. Or, and then instead of doing this, I'm gonna do oh yeah, I might need something similar here, where I'll do define assert handler. Why did I do this again? Oh yeah, to take advantage of the formatting here. Yes. Oops, sorry about that. Okay. So here we'll do this. We'll call assert helper along with the VA args, and I want, what should I do here? Maybe what I'll do is I'll go const char star file int line and then message. So assert handler, assert helper will take file line message. Okay, like that. Now assert helper will take the stringized file line. So that looks similar to here. Oh, I guess no, this is already stringized, nothing to do there. That's an int. Pass it, and then do I really need to do this? Assertion failed here? I guess so. With the condition and what would end up being an optional message, which is cool, with the args. Okay, something's not right here. I got probably like a, I think I'm just missing a parenthesis at the end here. Yeah. And there we go. Client format reformatted everything for me, which is nice. And that's it. And there's no parenthesis at the end. Sorry, no semicolon at the end because I want to be able to put my own semicolon. I wonder what they're passing here, what their W assert. Oh, actually, it's right above. They've got message, file, and line as an unsigned int. What's this 0 for? Oh, they're using the comma operator. Okay, so they're injecting this, and then after that, they want it to evaluate to 0, and they want to ignore the fact that this evaluates to 0. Just thinking about why that is. Is it because in case somebody tries to use this assert in a conditional? Or is this more about, this is probably more about avoiding warnings. By saying this expression always evaluates to 0 and then they just cast it to void, that probably shuts up the compiler warnings or something. So, you know what, let's do the same thing. Because if Microsoft is doing it, there's probably a good reason to do it. That's probably what I was saying. Is that right? Yeah. Okay, so let's see if that actually compiles. I think I had some asserts here that I deleted, but now they're back. Okay, so it doesn't seem to like what I did here. Yeah, it's got some, right, of course I gotta actually do something in here. All right, so that's not bad. Printf assert I will definitely replace these logic errors that I'm throwing with some proper class I'll derive, and this way I can catch my specific one or something. Don't really care right now. Actually, this is not as cool as I thought. It would be nice to package up the file and line number here with the message, but I don't want to like have to format twice, so maybe I don't think I have much choice, actually. I'll remove the assertion failed here. Okay, yeah, you know what I'm gonna do? I'm gonna do like this. File, line, condition, and then the message. This will have already been formatted, and then I'll format the rest into here. Yeah, that's what I'm gonna do. So file, line, the stringized version of the condition in here. The message will just be the VA args. Okay. So now, and since I called my assert helper here, oh yeah, gotta pass condition, message dot dot dot, condition. Then here we've done the formatting. So by the time we get in here, the message has been formatted with the user's formatting. And now we want to do another formatting. Something like this. Assertion failed, condition. And here I can do a bit more fancy formatting if I want. Condition %s. File. I'll do file and line. %. Yeah. And then finally message. All right. So first I need the condition, then I need the file, the line, and the message. So we'll printf this guy, and we'll throw it this way as well. Does that build? So what have I got here? Formatted string 1024, no appropriate default constructor available. So it doesn't like what I did here, right? Is it because I'm copying it? Const autoref, yeah. There we go. No. Note: no constructor could take the source type or constructor overload resolution was ambiguous. And then assert handler does not take 3. 1, 2, 3. Where am I calling assert handler? File line condition formatted string. One file line condition. What's it complaining about? A note assert handler function does not take 3 arguments. File line condition args. File line condition. Then this is the message and the dot dot dot. Let me see something. Try and narrow this down because it's always fun with macros. No, so it's not that. Looking for a default constructor somewhere. Trying to figure out why. Why is it thinking that I want a default constructor for formatted string? These are all const char star. The constructor here takes the format as usual. Okay, let's try something. Let me make sure. Is it this one? So if I pass an empty string here, will it complain? Okay, so maybe it's something else related to this next error. Illegal write operand has type void. Oh, right. It needs my assert helper to actually return a Boolean value. So I assume that's what they're doing here. Okay, I just understood. Okay, yeah, I got this wrong. Now I understand what the comma 0 is for. Yeah, okay. So actually, I need to close this here. Then it's or, and it's, we want to call some function, but we need to comma 0 here to make this logical or happy. It wants a Boolean result, so with the comma operator and 0, or I could put false here. Basically, that'll shut up the compiler. It'll say, okay, it'll allow this to happen. Allow us to be able to put a conditional or, a logical or, I mean, here. And what's the problem now? Yeah, that should be good. Just see how Clang format would format this. Yeah, that's good. Oh, did I not do that right yet? no, sorry, this should be here. Yeah. Okay, so now that compiles as it should. Let's put this guy back in and see if we're still getting that error from the formatted string default constructor. Yeah, so still getting that. Why? What is it that it doesn't like? We're taking file line condition. Assert handler here takes file line, which is an integer, I think. Maybe it's not. But I noticed that they were casting it to unsigned. Anyway, so file as a string, line, let's say as an int, condition as a string, and then va_args, which would be basically message here, ... right? Mm-hmm. Yeah, absolutely. So that would work. File line condition, formatted string. No idea. No idea what's going on here. What I don't understand is that this is the same thing pretty much as my fail here. Oh, right. Yeah, the problem here is that in this case I'm not passing a message. So this va_args is 0 parameters. Like there's no parameters here. Okay, so I'm just thinking, what is it I want to do here? Okay, so I want this to be optional. Sorry, getting some texts. Okay. what is it I doing again here? I use fail sometimes with messages, right? And I just pass it straight up to fail helper, where the VA_args is itself the message. Oh yeah, and the trick is to pass an empty quote in case there's nothing, and then that just ends up being nothing. Right. Like that. Am I wrong? Saying it doesn't like the comma. That's it. So we pass nothing. This will be nothing. What am I not seeing here? Now it's complaining about syntax error, comma. What is it doesn't like? It's not that. This comma? Let me just like reline this up so for my eyes. Okay, so there's that or that. And then that goes with that. Yep. Yep. This all makes sense. I don't understand what's going on here. That's why I hate dealing with macros. But for assertions, you kind of have no choice. Okay. Actually, you know, it looks like if my assert has a message, it seems to be okay. So this is related to the situation where I have no message, in which case VA_args here expands to nothing, and so maybe it doesn't like I guess because that's it. I always, okay, all my fail macros always have a message. Yeah, that's what it is. I don't really I don't have a clean way to handle the case where if VA_args is nothing, then yeah, that's it. If this is not passed in, then it just sees this empty comma. It's like comma, comma, and then that's what it's complaining about. If I don't put this part here, then I still can't pass nothing, because then I'm calling with an empty message when I call my assert handler. So maybe I really have no choice. Maybe I need to have a version of assert where I must pass a message, where I can pass a message, one where I don't. Or maybe I just force it to always have one. Nah, that sucks. I don't know. Like it would be something like Like if I have assert message, then I definitely pass the message in optional arguments. Otherwise, assert here takes nothing extra. So then I don't need any of this. Although I probably have to pass in empty here just to be able to call my assert helper. Although in this case, I don't really need the assert helper. I can just call the assert handler directly with no message. Do this. Something it doesn't like. Assert condition, that's what I'm doing. What did I miss here? All right. File, line. So technically, these shouldn't even compile. Do they? Yeah, they shouldn't compile because there are too many parameters. But if I do message here, then these will compile. And now I can bring this guy back, which has no message. That also works. Now I just need to handle the case where null was passed in. So, okay, let's bring this all back online. Message, I'll do this. If message is equal to null pointer, I'll just say NA. Otherwise, I'll put the message. So let's see what that looks like. Okay, so assertion failed, condition A equals 1, file 17. Maybe I won't put that space here. Message, there is none. Not available. Hit the next assertion here. Okay. All right, that's pretty cool. I may just put a little tab for these guys, or maybe just a little space. A single space should do, just to like make it look like a block. Come back here, make sure this looks clean. So yeah, technically this assert helper was really only for this version here. So now the only thing I don't like is that we're back to the fact that fail really always takes a message and should really be fail message. So that it's like assert or assert message. So I'll just put a little to do here. Message. All right. And what did I want to try here? To try this again. Just want to see what it looks like. Okay, that's nicer. Oh yeah, I wanted to remove that space. that. This is neat. This, just remember this. Need this helper for Clang GCC so we can pass a single arg to fail. Right. Just gonna shut up my phone. Okay. All right, pretty happy with this. So we've got assert with just simple condition, assert that takes a message. I'll do the fail thing afterwards. So now the question is, which asserts do we want to replace? You know, and it's got to be the ones that I think can actually fail, like at runtime. You know, so actually something like this. Yeah, and actually this is a case where we would want to use fail. Unmapped address, but see again, not going to happen, right? Not really. Well, could happen. So okay, I'll put it here. This really should be a fail message, but I'll do that as a separate step. Okay, these assertions are just programmer checking programmer errors, so that's fine. All the stuff in stream is okay. Yeah, again, programmer error check, not gonna happen. Programmer error check. So because I have asserts for stuff like, you know, sanity checks for my code, make sure that my assumptions are valid, but it's not something that would happen at runtime and that my debugger would have to catch, really. Same. Same. So these are assertions that are just validating that, you know, that the instruction stream would have, like these are, this assert here has to just do with, like, by definition, how this instruction works. It must be one of these cases, 8-bit to 8-bit or 16-bit to 16-bit for transfers. And if this were ever to fail, it would mean that the ROM is bad. And it's not some kind of error in my emulator or some user error. So I'll leave that alone. Same here. What's this again? Execute instruction. If I have a op who cycles, okay, so if I have an operation whose cycles are not yet greater than 0, look at how to handle cycles for this. Is this really a real thing? CPU op codes. Did I actually have something like that? So we're looking at cycles. Cycles would be this here. I'm really curious that I did that. I don't see any zeros in there. Maybe I had zeros at like one point, and to see like this column here, let me just hide this. This column here is all, this is what we're talking about here. Actually, what I could do is I could search in this column for a 0. Whoops. Can I do that? Yeah. Find in selection 0. Okay, there's no 0 in there. So I think that's moot and useless. Oh, there's 20. That's okay. And those zeros here. Okay. So this was useless. I guess this was valid at some point. Doesn't really matter. I'll leave it alone because I don't care about that. Okay, so illegal instruction, definitely. This is definitely something I want. In fact, Here now I could do a little bit, something a bit more interesting. So illegal instruction. So we'll do like this, right? We'll say illegal instruction. I mean, I'm gonna see it, but I'll just put, at least I'll put the name. Although I don't think these even have names. To be fair, I don't think these instructions that are illegal even have names. Let's go see. Yeah, they're actually called illegal. So actually that's a bit useless here. I'll just put illegal instruction. So we got the assert message there. That's good. Again, this here, this is just a normal assert. Kind of sucks to have to make this distinction between the two, right? I don't know. Should I be bothering to make a distinction? Maybe not. Fuck it. I'm not gonna do that. I'm just gonna use my asserts. There we go. Stop thinking about it. And what I could do is, like, you know, for my final release of the emulator where I don't want the debugger and all that, I could turn all these asserts back to the basic assert, like the default one from assert, and then it'll be optimized out or whatever. So yeah, like I really only want my assertion for when there's a debugger enabled. So I'll probably have a way to build it without debugger, and in that case I'll just fall back on the default assert. This should be an assert message. Oops, sorry, not like that. Yeah, and then this here too. Okay, so that's all the asserts for the CPU. I'll look for assert, assert case. Anything else in memory map? No, that's good. Stream, I'll leave those alone. Okay, so here's my debugger. This should just be a fail. See here, I'd want to fail without message. What's this? Debugger. Yeah, I'll just put assert here. Fail. Unexpected addressing mode or something. Where are we? Platform. Okay. I think I'm going to leave this alone because it's the platform stuff. Okay. So now Okay, that's it. That's it. This is good. So now, like, if we look for assert and caps, we've got a few in the CPU and a few in the debugger. These are really the ones that if I would hit these while debugging, now they'll end up throwing. They'll print to the console, but they'll also throw an exception, which my debugger has a try around it. Yeah, and execute here. Sorry, try, and I have a catch here. I should beef up this catch a little bit because now that I actually am throwing an exception with a message, even though my printf already prints it, maybe I'll end up removing that printf eventually. So, or maybe right away. I don't know. I'll just do this. If we catch a standard exception, exception caught, the what? Okay, so actually, if we catch an exception, we'll fall out and come down here. Otherwise, we will have returned already. So I can just do this. That makes more sense. Unknown, I'll just put like unknown exception caught. Otherwise, exception caught, blah. Is this build? Yeah. So I mean, I don't think I have an example. What I could do to make this, to test this, is I could just like, apart from the ones that I have here that I'm kind of forcing, I'll take one of these instructions, like, you know, bit B, and just not implement it and like see what happens. Bit B is 0xc5. Okay, so these are the bit. So let's just take all these out. Pretend we're not handling them. And actually, you know what? Let me take out these exceptions now in main. I don't need them, these asserts. Okay, so now we should hit an assert. Boom, here we go. Unhandled exception bit B. And then I say exception caught, unhandled op, bit B. So this is actually not an assert, it's a fail, but similar. I would like to actually trigger an assert. Another thing I noticed is that I should, in my try catch here, put a /n after I print the what message. Now, come back to CPU. Just for kicks, I'll change this to an assert message. False. Unhandled op. I'll just do the same thing because I just want to see what it looks like when I hit an actual assert. All right, assert failed, condition, exception caught, and of course the exception is an assertion. Yeah, so it looks a little funny, but you know what? Too much information is not a big deal. I'm trying to think, like, is there a case where I'd want to print and where I'm not catching exceptions? Probably not. So maybe I'll just remove the print for now. This way I don't, if I ever need to put it back, I'll put it back. I don't think I need it though, since I'm always catching and printing. and I'm throwing an exception with the whole body of the message anyway. So if my debugger catches it, I can take a look. So it's all good. Okay. So that would be in base here. We'll take off the printf. Same thing here. So in which case I'll simplify this to that. Yeah. Good, good, good. Let's try that again. Okay, so exception caught, assertion failed. And there we go. And see, the good news is that I'm still here. I mean, I'm at the next instruction, right? Because the CPU just says, oh, how many bytes is this? And advances us to the next one. It's 2 bytes, so she's not even, yeah, I'm like totally in the garbage instruction, I think here. I think I only advanced 1 byte because that's it. I advanced 1 byte after I read which op it is, which was bit B, and then we looked it up. Oh, and then we got an exception. That's okay. I don't really care about being able to continue. I am able to look at the registers. I can print memory values. I don't expect to be able to step. Like if I step now, something weird will happen. Like it interpreted the next instruction as test memory location, which is incorrect at this point. But at least the advantages I get from having thrown this exception, caught it, is stuff like the buffered output that we're getting when we run the debugger. It will flush the buffered output and show me exactly which instruction failed and everything. So this is exactly what was the point of doing all this. Yeah. So I'm pretty happy with that. And now, you know what? Yeah, I'll do the fail right after. Let's get this checked in. I think this is definitely in a good state for checking in. So base, fail handler, assert handler, looks good. So let's stage that. BIOS ROM, stage it. Cartridge stage. CPU's got a bunch of fails and asserts in there. Oh yeah, let's bring this guy back. 850 on the CPU. Ah, yeah, bring back 1534. What's the deal with that? Huh. Why would it format it that way? Interesting. Like a weird bug in client format. It wants to put it there, but if I put it here and save, it doesn't do anything to it. Super weird. Okay. Okay. So that's good for CPU. Now debugger. Okay, so I want everything except for my little change at the bottom. Okay, cool. So I'll put here, implement custom assert message macros that throw exception, so that debugger can catch them. Useful when debugging to make sure stuff like flushing standard out happens when when certain errors, certain asserts trip. Okay, so that's done. And while I'm in that mode, let's fix up the fail macro to be a little bit more consistent. So we'll want fail and fail message. So fail message will be the one that takes the message. Don't really need the fail helper for this, so we'll just call fail handler. Honestly, at this point, I'm even wondering why I would want a fail handler. Kind of want similar information, right? Like I'm considering here just maybe calling assert handler, going the other way around, you know? Had a thought. Could I make this a bit cleaner? Rather than calling assert handler and passing null pointer directly here, I think I can make my assert helper a bit smarter. If we assume message is a const char star, I can kind of do the trick here that's like pass message like if message is valid, do this to it, otherwise pass message, which is the same thing as saying message and this. No, that I don't want a Boolean expression. So I'll just do like this. If message, do that, otherwise pass message, which is actually null, so I guess I could just do this. And in that case, I can like reuse this here, which I kind of like better. And we'll see why, because I'll be able to use it for fail. Like that. Okay. Okay. I'm not going to test it again because it'll work. So then in that case, I'll just make fail the same thing as an assert false. It's okay. The condition will be false. It's okay. So we'll have fail that takes no arguments. So actually this one here will become a fail message. We'll have fail that takes no arguments, and they'll both do the same thing here. They'll just call assert helper. So the one that takes no arguments will have no condition, or it'll pass false as its condition. It's a bit weird. That's okay. So basically, if we just do a fail with no parameters, we just want to call, it's like calling an assert false. So why not just call assert false? Okay, this is build. No, this won't build because I have fails that take parameters, so I'll get a whole bunch of errors. Yeah, about too many parameters to all my macros that are fail macros. So what I want to do is I want to replace all of those with fail message, except for the ones that where I'm not passing anything. Fail message. Like that. Okay, so everything builds. Just want to try having it run a bit. Let's test that case I did before in the CPU where unhandled op here. Yeah, so let's take the bit again. Let's hide this. Okay. All right, so there we go. See, so this is a case where we got assertion failed, condition is false. which means basically it's a fail. I'm not really checking any condition, but it tells me exactly where to go look. And the unhandled op is bit B in this case. So it's an unhandled operation. Perfect. I'm pretty happy with that. Okay, good. In fact, let me just build once and release, because I want to make sure I'm actually not doing anything in release. I should be removing these asserts in release actually. But I will not. I'll worry about that later. You can see it's already much faster. Turn off trace. Okay. Yeah, so what's good is that even when I'm running in release now, if any of these trip, I'll definitely get an exception. It does mean there's a runtime cost. I'll worry about that later in the sense of when I'm actually doing rendering and I need this to be timely. If release doesn't actually run fast enough, I'll definitely address the fact that my assert macros are present in release builds. But for now, it is totally fine. Okay, that's good. Good. CPU. All good. Debugger. Everything except for the bottom here. Okay. Refactor fail into fail and fail message, and rewrite in terms of assert. Good. Just want to look at these again. Okay, so I just have here this debugger thing with the frequency. I'm gonna encode that and commit it. What I'd like to do here, because I'm tired of having this change hanging around, 859. So for now, I'm just gonna have like a macro that's like if, what do I want to call this? If force fast forward, we'll do this, else for now, I'll just do that. Just waiting for the IDE to highlight this one. Okay, there we go. This is just like some code where I'm forcing the CPU frequency to be like extremely high so that it runs as quickly as possible, which is what I want for now while I'm developing. This won't last long, and what I want to do is I want to keep it at the correct frequency and then have some way to like toggle or hold a key or button to make it run as fast as possible or something temporarily in like a fast forward button. But for now, this is fine. While we develop, we'll do this. Force fast forward mode by default for now. So that leaves me with this little comment I started writing in the via. I'll leave that because that's what we're going to start working on. Okay, all right, that's pretty good. I spent the first hour and 15 minutes just doing this assertion stuff. It's amazing how long things take. Would never have thought it would take this long, but there you have it. Let me just push this. So actually, I'm just gonna go grab some water, and when I get back, we'll start working on reading about the via and starting to implement this chip. So I'll be right back. Okay. Let's see. Let's put this here. Oh yeah, stop my music. All right. Make sure everything's okay here. Okay, cool. So the VIA chip. So the VIA chip, which is this 6522 versatile interface adapter, it's basically this chip that the CPU in the Vectrex interfaces with via memory mapped registers. And what it does is it's used to control all the peripherals. So what they call here the keypads, which is like the two controllers that you can connect in. There's the vector generator. So that's basically for rendering, for drawing the vectors on screen. There's a digital to analog converter in there. I think that's related to the vector generator, if I'm not mistaken. There's also the sound chip is connected to the VIA. And I think from what I read, this chip was actually 6522, was it? This chip is actually, here we go, MOS technology 6522. So it looks like this. Yeah, so it was designed and manufactured by MOS. It has an I/O port controller for the 6502 family of microprocessors, although that's not our case, but provides, or is it? No. Anyway, it provides two bidirectional 8-bit parallel I/O ports, two 16-bit timers, one of which can also operate as an event counter. So still learning about that. And an 8-bit shift register for serial communications or data conversion between serial and parallel forms. The direction of each bit of the two I/O ports can be individually programmed. So I read a little bit about this. Basically, the first two ports there, the 8-bit ports that they talk about here, they're bidirectional. And there's like a bit that you can set that says whether or not they're in, input or output mode. So whether we're going to be writing to them or reading from them. In addition to being manufactured by MOS, the 6522 was second sourced by other companies, including Rockwell and Synertech. Okay. It was widely used in computers of the 80s, particularly Commodore's machines, and was also a central part of the design of the Apple III, Oric 1, and Oric Atmos BBC microcomputer, and Apple Macintosh. Video game platforms such as the Vectrex also used the 6522, as did the 1984 through 1989 Corvette Digital Dash cluster. Oh, no kidding. That's interesting. Okay. So, oops. So the VIA contains 20 I/O lines, which are organized into 8-bit bidirectional ports. So I guess they're talking about these 20 lines here, 1 to 20. And into two 8-bit bidirectional ports, or 16 general purpose I/O lines. So I think when I look here, it says like PB0 to PB7, and then, no, sorry, PA0 to PA7, PB0 to PB7. So those are the two ports. There's ground over here. Then CB0, CB1, which are, it's kind of small. Yeah, that doesn't help at all. Okay, anyway, it doesn't matter. So what does it say here? So the control lines can be programmed to generate an interrupt. Oh no, sorry, I was here. Which are organized in two 8-bit directional ports and 4 control lines for handshaking and interrupt generation. The directions for all 16 general lines can be programmed independently. The control lines can be programmed to generate. So what does that mean? The directions for all 16 general lines, PA07, PB07, can be programmed independently. So I think they mean for A or for B, right? Not for each line. Maybe they do mean for each line. That's interesting. The control lines can be programmed to generate an interrupt when activated, all 4. Latch the corresponding I/O port, CA1 and CB1. Automatically generate handshaking signals for devices on the I/O ports, or operate as plain program controlled outputs. CB1 and CB2 are also used as the clock input and data line for the shift register. CB1 and CB2 are also used as the clock input and data line for the shift register, precluding their use for other functions while the shift register is enabled. Okay. So they kind of like double up, basically. The VIA provides two 16-bit timer counters. Each can be used in one-shot, monostable interval timer mode. Timer 1 can also be used in free-running divider square wave mode, in which the timer is automatically reloaded with the initial count when it reaches 0. Yeah, so first thing I want to say is I am actually not a hardware person. So like I didn't do any hardware in school or, you know, as a hobby. I didn't study computer engineering or electrical engineering. I studied computer science. So everything I know about hardware is just purely out of interests and what I've read. And actually, a lot of this is not like super comfortable for me. So part of the fun of writing this kind of emulator is for me to learn a bit more about the hardware, because I find it really cool and interesting. And I started doing some reading about timers, like what they're talking about here, these like interval, one-shot or monostable interval timers versus these timers that can reload. I actually had found this pretty nice page here, Introduction to Counters Timers, that kind of shows different kinds of hardware timers. And it talks about it in here about semi-automatics, which are timers that have automatic reload capability, will have a latch register to hold a count written by the processor. And when the processor writes to the latch, the count register is written as well. And when the timer later overflows, it first generates an output signal, then it automatically reloads the contents of the latch into the count register. So that sounds like, and then since the latch still holds the value written by the processor, the counter will begin counting again from the same initial value. So basically it's like a little piece of memory, which they call the latch, that when you write to, it immediately resets the counter to the same value you write in the latch, so upon write. And then when the counter reaches 0, or when the 0 reaches the count, depending on how it's implemented, it gets reset to that value that's in the latch. There's also another one here they call the input capture, which is slightly more advanced. An input capture timer, like the one shown in figure 2, has a latch connected to the timer's count register. The timer is run at a constant clock rate so that the count register is constantly incrementing or decrementing. An external signal latches the value of the free running timer. An external signal latches the value of the free running timer into the processor visible register and generates an output signal, typically an interrupt. So I think this is kind of like an event, what they're talking about. You know, there's a way to say generate an event every time it reaches some, when it reaches the count that we're looking for. So it says here, one use for an input capture timer is to measure the time between the leading edge of two pulses. By reading the value in the latch and comparing it with a previous reading, the software can determine how many clock cycles elapsed. In some cases, the timer's count register might be automatically reset just after its value is latched. If so, the software can directly interpret the value it reads as the number of clock ticks elapsed. An input capture pin can usually be programmed to capture on either the rising or falling edge of the input signal. And then it says there's all kinds of options. So trying to wrap my head around that, it sounds like we have a kind of advanced timer here. It's a 16-bit timer. So if we read here, the VIA provides two 16-bit timers counters. Each can be used in one shot, interval mode, timer 1 specifically. So there's two, timer 1, timer 2. Timer 1 can also be used in free running divider square wave mode, in which the timer is automatically reloaded with the initial count when it reaches 0. So this is a down count timer. And timer 2 can also be used in pulse counting mode, in which the timer will count the high to low state transitions of pin PB6, the 7th bit of parallel IO port B. So PB6 up over here. So pulse counting. So it's going to count pulses. So if this guy goes from on to off or high to low, it's able to count that if it's in pulse counting mode. In the one-shot mode, each timer continues free running. In the one-shot mode, each timer continues free running so that the time since 0 was reached can be determined. Right. That's interesting. Okay, so in one shot, let's say it reaches 0, generates an interrupt, but then it keeps counting. So I wonder, I guess it underflows. So, but no further interrupt is issued until the timer is restarted. This is really about getting interrupts. Each timer can generate an interrupt when it reaches 0. And timer 1 can also output pulses in the interval timer mode. Okay, yeah, sorry. Interval timer mode. Or square waves in the free running mode. Okay, I'm just kind of wrapping my head around because they keep using the same terms. One shot interval timer. Okay, so they're calling it an interval mode. It's interval timer because it's the idea is to count intervals. But that's what they mean by interval timer. So it's the one shot versus free running, which is over and over. It'll just keep generating interrupts, not just once. So in the one shot mode, each timer continues free running so that the time since 0 is reached can be determined. Oh, sorry. Each timer can generate an interrupt when it reaches 0, and timer 1 can also output pulses or square waves in the free running mode. So I guess what they mean here is in free running mode, it can generate a high signal over a certain period of time and then go to low for a certain period of time. That's what they mean here. That's very interesting. So that would not be for interrupts. That would be for, like, if we want to read a square wave off one of the output pins, we would get high for a while, low for a while, high for a while, low for a while. On pin PB7. So PB7 would be the one that we'd have to read. Timer 2 can be used to provide the clock frequency for the shift register. Timer 2 can be used to provide the clock frequency for the shift register. So I guess that's how often it needs to shift over time, the value in the shift register. A useful feature of the free running mode is that the 16-bit counter latch can be loaded with a new count without reloading the counter. Okay, so that's different from what I was reading on that other page. So while it's counting down, you can go and write a new value that won't reset the counter. It'll keep counting, but when it reaches 0, it'll load that new value. So that is useful. Okay, so I got to make sure I implement that correctly. Seamlessly changing the output frequency. Right. This feature of timer 1, combined with its ability to output to pin PB7, can be used to generate complex waveforms. For example, pulse width modulation signals, frequency sweeps, or biphase or FM encoded serial bit streams. Okay, that's cool. Makes me wonder if that's what's being used to do the audio. Okay, like right now I'm just reading the general, like how this chip works, but I also need to kind of read, and I have some docs on that, on how it's used by the Vectrex. It may be simpler, you know, like we may want to only implement a subset of its functionality because only a subset is ever used by the Vectrex. And since what's interesting about the Vectrex is I don't think any of the games directly interface with these chips. They might, but I'm not sure. But I think what happens is that all the games they tend to use the BIOS routines. So really what we're interested in is the way the BIOS routines use the VIA. So if they're only using like a subset of these features, we only have to implement those for the games to work. Unless the games like bypass the BIOS altogether and do their own thing, in which case then we'd have to implement all the features. So we'll see how that goes. Okay, just give me a sec. Yeah, shift register. The VIA's shift register is bidirectional, 8 bits wide, and can run from either a timer generated clock from timer 2, which is what we read earlier, the CPU clock, or an external source on line CB1. So this is where we would like to know how it's done in the Vectrex, for example. The serial input output is on line CB2, and CB1 can also be programmed to output a bit clock for external clocked serial devices. Okay, so what I think this is, so a shift register is basically a register where at a certain rate or under certain conditions, the, let's say, low order bit will be read, whether it's a 0 or 1, and then all the bits above it will be shifted down. And so as we read, you know, we will get the 1 bit at a time. And it sounds like, you know, the rate at which the bits are progressively shifted can be controlled by clocks, for a timer generated clock or the CPU clock, or they say an external source on line CB1. So something else can kind of pulse the shift register to tell it, go ahead, shift, shift, shift. And then they say, you know, to read the serial input output is on line CB2. So on CB2, this pin, we can write bits into it. That's another thing. I think we can write 1 bit at a time, which basically every time you write one, it shifts left, or you can be reading 1 bit, I think. And CB1 can also be programmed to output a bit clock for external clocked serial devices. Okay, not 100% sure yet what that means. Due to a design defect, if the edge on CB1 falls within a few nanoseconds of the falling edge of the O2 phase 2 clock, the CB1 edge will be ignored, causing the loss of a bit and framing errors in subsequent data. As a workaround, put the external clock signal into the D input. All right, this is more information that I need to know, I think. Okay, so this is the interrupts request. This is the interrupt here. The NMOS 6522 has an open drain IRQ output that may be used in wired or interrupt circuits. Okay. bugs. Interesting. Aside from the aforementioned shift register bug, there was a potential register corruption problem that usually only occurred in systems using the 6522, with a microprocessor having a non-6502 bus architecture, such as a Motorola 68000. Now that's not our case, because ours is like a predecessor to the 68000, right? It's a 6809, but maybe it is also something that happens in the Vectrex. If the address line changes while chip select was low, but the phase 2 clock input was high, register contents could be changed despite the fact that the chip was not selected. This was fixed in some, but not all of the CMOS versions. Okay. So this gives like a high level overview of what this chip can do. Now, what do I know? I have this information. So the BIOS that was disassembled by someone, Christopher Salomon, and then later on by a few other people, it has, like, I know that basically if we look at the memory map, the VIA here is 16 bytes shadowed 128 times. So basically there are 16 bytes starting at D000 to, D0 0F. So those 16 bytes, which then get shadowed 128 times, so we don't really care about that. That represents the 16 bytes of memory mapped registers to the VIA itself. So that we know. In fact, we even know that the dude, what we call the dude register, D00D, is something that I set to FF every time I run my emulator right now, because if we don't, we end up with an infinite loop very early on. And here we have this mapping of the VIA ports and registers and all that, which is very useful to kind of give me a high level understanding of what we need to do. The dude register, which is here, is the VIA interrupt flags register. I just set this to FF, which is all on, and that gets us fairly far into, past the BIOS and into Mindstorm or whatever cartridge game we have. So obviously I want to stop doing that and I want to implement this properly, but it's useful to look here at the names of what we got here and kind of like, map that to the information that we're reading here, right? So like we see, for example, port B is the first one, and port A is the first byte, so at 0, and then at byte 1 is port A. I don't know why these are inverted. On the chip itself, A does come before B, so seems arbitrary, but it is what it is. And then the next byte is port A data direction register. Here. So port B is the port B data IO register. And then port A is the port A data IO register. And it says handshaking here. And I wonder things like port B here is broken down into all the 7 bits. And I wonder if port A is similar. Does it use, does it have the same thing for port A as it does for port B? It might be, since they're both data IO registers. Then the next 2 bytes are the data direction registers, these DDR registers for B and for A. And it's interesting because, okay, so this makes more sense, because I was wondering, why is there a full byte used to control like whether A or B are input or output? It's not like that. It's actually each bit of this byte controls whether each bit of A and B are input or output. So that corresponds to what we read here, how like the directions for all 16 general lines can be programmed independently. So that makes sense. So whether they're input or output is you got to set those bits, right? Yeah. Okay. Then the next ones here are the via timer 1 count register low, which they call the scale factor. And I think this has to do with the fact that these are used to control the vector, it's just from memory, the vector rendering. You set this timer value to like how long I want the beam to move, and that's like a scale, you know, like if you set it higher, it will draw for longer because you're giving it more time to draw. So they consider that like a way to scale your lines. Now I don't know if it's a, you know, if it's a linear scale, so we'll have to see. But yeah, so that's basically, there's these 2 bytes, 4 and 5, are the timer 1 counter, low and high. And so that corresponds with the idea of having a 16-bit timer, right? And then the next 2 bytes is that same timer, timer 1, its latch register, right? The low and the high. So again, the 16 bits, sorry, the 2 bytes. This is the latch. This would be the value that we write to reset the counter. And yes, I don't know if it's also, yeah, maybe it's also for reading. Then here we have the second timer. But here, what I don't quite understand is it looks like the timer 2 here is both a count and a latch register. Okay, so I think what this is that timer 1 is one that has a separate latch, so that you, while it's counting, you can go and write to the latch. It has its own separate, you know, memory for that, and it'll read that when it reaches 0 to reset itself. That's like that special feature I was saying down here the timer 1 has. Let me see. A useful feature of the free running mode is that the 16-bit counter latch can be loaded with a new count without reloading the counter. Now, that's free running, right? Timer 1 can be used in free running. So that, see, only timer 1 can be used in free running mode. So that corresponds to my understanding here. The timer 1 is a more sophisticated timer. It has a separate register for its latch, whereas timer 2 is both a counter and a latch. So I believe what that means is if you want to reset counter 2, you just write to it, and it immediately resets its counter to that latched value, to the value you wrote into it. I think. Just reread here. Timer 2 can be used in pulse counting mode, in which the timer will count the high to low state transitions. Sure. Timer 2 can be used to provide the clock frequency for the shift register. Okay. This feature of timer 1, okay, so this comes back to what I was talking about for the special feature. Yeah, so timer 1 is definitely more advanced than timer 2. Okay. And then next one here, via shift register. So this is the shift register that we were talking about. So yeah, that's the shift register. And the via auxiliary control register. So for this one, we actually have a breakdown. There's auxiliary control. There's also control register, the next one. Interrupt flags register. Interrupt enable register. And then finally, what's this one? Via the port A data IO register. So port A data input output register. No handshaking. Now if we go back up here, auxiliary control register has a bunch of bits. So this is PA latch enable, PB latch enable. I wonder if what that means. I wonder if it means that when you enable the latch, then the value in there doesn't change. I have to read more about that. 2, 3, 4. So here it's showing that if you write 110, so this is shift. Okay, so these 3 bits here are the shift register control. So these are bits used to control the shift register. And then here it says 110 is the only mode used by the Vectrex ROM. So this kind of goes with what I was saying about, like, you know, specifically on the Vectrex, the BIOS probably only sets this shift, you know, these 3 bits 110. So that's the only one we really need to implement or support, probably. Where 110 means output to CB2 under control of phase 2 clock. So yeah, we were reading about that here, right? Where was it? Control of phase 2 clock. I think it's here. The VIA shift register is a bidirectional inputs wides. The serial input output is on line CB2, and CB1 can also be programmed to output a bit clock. Sorry, due to I saw this phase 2 thing somewhere earlier, didn't I? So it was only here. Output to CB2 under control of phase 2 clock. Okay, anyway. So then these bits here, okay, so these set the mode for the timers. So this bit here says, does timer 2 run in one-shot mode? If it's 0, or it runs in free running mode. And then this one is for timer 1, one-shot or free running as well. And this one here for timer 1, disable the PB7 output. Yeah, so we saw that timer 1 can output to PB7 for doing like the square wave stuff. Yeah, can output pulses in the interval timer mode, or square waves in the free running mode. So either or, pulses or square waves. On pin PB7. If it's 1, it enables that PB7 output. Okay. So that's the auxiliary control. So the auxiliary control is really, I mean, I don't know why it's called auxiliary control. And what's the difference between like calling it that and calling this one a control register over here? Seems a bit odd. Because here we've got like stuff to control the shift register, stuff to control latching on A and B, and stuff to control the timers. Okay. Otherwise, okay. the control register says CA1 control. CA1 to SW7. Let's take a look. This has to do with interrupts. If it's 0, IRQ is on. IRQ happens on low. If it's 1, IRQ happens on high. So SW7, I think that's SW7. What is that? I'm not sure. And then the next 3 bits seems like there's only 2 configurations to worry about. If this bit is 0 or this bit is 1. Okay, let me just see here. CA. The control lines can be programmed to generate an interrupt, when activated. All 4. So all 4 of them can be programmed to generate interrupt when activated. Latch the corresponding I/O port, CA1 CB2. Sorry, CA1 CB1. Automatically generate handshaking signals for devices, or operate as plain program controlled outputs. Okay, I really got to read a bit more. So I mean, maybe this is not the right thing to read. This is kind of like just some comments, but it's kind of getting some stuff into my head, and I'll clear this up as I read more about it, because I have other documentation here. I have a document about how to program this chip. Which also gives a bit more details on how it works. Like one thing I saw in this other document here is where is it? There was a nice table. Oh, no. Oh, it's right here. So this is the register addressing table, which corresponds to what I'm looking at on the other side. Basically, it just shows that there are 16 registers and the designation of each register. So like, for example, as we saw, the very first one, D000, which is a via port B, is output register. So it's output register B, or also known as input register B, because it depends on whether or not we're in write or read mode for each bit, right? And that's controlled by the data direction register B here. So like the ordering here lines up with the ordering here, so that's good. So one of the things I wanted to do is just like purely out of interest's sake is to kind of get a feel for which of these registers are being written to or read from. I mean, I know for a fact that that D00D, the interrupt flags register, is obviously being read, but I don't really know about any of the other ones, and I'm curious to see like what frequency and how often, like what frequency they're written or read from, which ones, and that's just going to give me an idea of like which ones we should be tackling first. Like I don't want to just be like blindly implementing a bunch of logic for this chip. I'd rather, kind of like for the CPU, implement something that looks like it's actually going to be useful, right? So I was thinking about, you know, there's a few ways I can do that. Like right off the bat, you know, I could just, I have the ability to set, you know, breakpoints. I think it's a break. Sorry, help. What was it again? A watch. That's it. So I can look for reads and writes. I mean, this will be a very annoying thing to do here, but just as a, you know what I'm going to do is I'm not going to do it in here. I'm going to do it in Notepad. A watch D00 0 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 and 4 5 6 7 8 oops 8 9 A B C D E F. Okay, so this just here will just give us like, we've got watch points, read write for all of those 16 registers, right? So if I just basically continue, we hit here, watch point hit at D002 and at D003. Yeah, I have this issue where I'm getting my watch points because they're like, because my disassembler does this, you know, work of trying to be helpful and writing out values. Like for example here, DP is currently D0, so it's set there, and PC, or sorry, the value at PC is 02. So D002 is 0, and we're trying to store D there. So actually, this is correct, right? We want to store a 2. So why am I getting 2 watch point hits here? Ah, right, because we're storing a 2-byte value, right? If I say store D, this is actually useful. See, 9FFF is being written to both D02 and D03. D02 and D03. So basically we're writing out to the what we want in terms of data direction for both B and A here. And what did we see? That it was 1 means output and 0 means input. So for A, it's all output. That's what this FF means. For B, it's 9F. Interesting. So like 9 means that, so we know the low 4 are all 1s. That's the F. The 9 says 1 here is 001. So if we look at B, no, sorry, that's it. 9 is for B. So 1001. No, sorry, 9F. 9F. So I guess, okay, so it would be like this. These are all output. This is output. these two become input, and this is output. Comparator input is an input. External device slot pin 35 initialized to input. Yeah, I don't have any idea what these mean, but that's what we're seeing. So we're seeing that we're somewhere in the BIOS where it's doing this. In fact, let's go look this up. F151. Here we go. So there we go. So it says init via. This routine is invoked during power up to initialize the via chip. Among other things, it initializes the scale factor to 7F and sets up the direction for port A and B data lines. There we go. Like, I get the impression that after this, they probably don't change. Maybe I'm wrong, but it seems likely. So here's our store D. So yeah, so load D, 9FF, it says port A, all output, which is what we just concluded. And then port B, 0110, that's not what 9F actually means. It's kind of the other way around, right? Yeah, so this looks wrong. That should have been 1001, then 1111, because that's what 9F is. Okay. Okay. And then the next write looks like it's going to be the port B. And there we go. So here we're writing to 000 and 001, so to the two ports. So that's it. We're loading this here, port B, sound, be there 1. So that writes to both B and A. A gets 0. B gets 1. It said here, sound direction. Does that go with what we saw? Write value of 1 to this guy. Why is that bit 4? Why is it saying bdir here? Curious. It's the low bit, right? Shouldn't that be this? So I'm not sure. I don't know if I can completely trust. Like, I don't know if I can trust this here now. So, you know, we'll keep reading. We'll get more clarification on that. But that's a bit strange. Then we've got here the auxiliary control register that's going to get some values. ACR98 T1 to PB7 enabled. 98, so ACR. Let me go look at this again, the auxiliary control. So this is actually going to write once again to two registers, this guy and this guy. The 98 corresponds to the auxiliaries. Okay, so ACR is auxiliary control. We're just writing 98 to it. And then we're going to be writing 7F to the control register, which says PB7 enable T1 to PB7, which is actually comes from here. Okay, so yeah, this is more related to the fact that we're writing 98 here. Okay, so there we have it. Sorry, what had just happened here? We loaded D and then we did a store A. Oh, sorry, yeah, store A. So this is only writing for first the auxiliary controlled. And it's writing the A portion, which is this. And then the B portion, which is 7F, will be written to T1 control low. There. Which is D004, okay? So now let's continue. All right, so now we're somewhere else. We're at F357. Reset 0 ref. This routine zeros the integrators and resets the pen back to the origin. It leaves the integrators in 0 mode, so nothing can be drawn until a move is done. Or D00C is set to 0xCE to bring /0 high. This routine must be called every so often to prevent your vectors from getting out of whack. So blank low and 0 low. So that's what this does here. 00CC. Store B there, store A into the shift register, clear the shift register. That'll be the next step. So there's the shift register, right? Okay. Next. Reset pen. Okay, so lots of resetting here. Store D. Where are we? F1A5. Set refresh. Just getting an idea for what's going on here. Move to IXB. Set scale factor. Okay, and now we're at that point where we're reading from the dude register and waiting for bits to be set. So I'm just gonna, that's funny, when you write to it, I get a watch point for the write. Watch point hit, yeah. Now writing's there. So yeah, lots of action on D0 and D1. Okay, that's interesting. Let's do something here. Let's go into VIA and let's collect some stats. So I'm just gonna hack this in because we don't want to keep this, but it's just more for information. We have 16 registers, right? And what I want to do is I just want to count the number of reads and the number of writes. So like static reads and writes. So if we get a read, We'll do this. And we get it right. Similarly, we'll just count it. So what I'm going to do is I'm just going to start this up, set do to FF so we get somewhere, turn off trace, and just run. Just going to run for a little bit. All right, so let's put a breakpoint here and execute instruction. So if I come back here to my main, just grab the via. Oh no, actually there are globals, right? So that's even simpler. Okay, super interesting. So let me actually note these down. I'm gonna take I have a notes here. So yeah, I started documenting here. Just started putting here the via from the Vectrex Inc. I just copy pasted all of those flags, but here we go. Like I put here initial number of reads writes of each via register after running for a minute or so with dude equal to FF. Everything else is actually 0 initialized, so all the other registers are 0, but this one gets FF in it. So let's see what this looks like. I'll clean this up soon. I just want to copy it in there. Okay. Yeah. Just cleaning it up a bit so it's a bit easier to see. Okay. Wait, did I make a mistake? No, that was fine. Okay. So in my little test here, reads only happen in 0 and 1, which I know is basically this corresponds to PB, this B, and this is A. I guess I should call it PB and PA, not to be confused with CPU. Caps lock. 13, what's that guy again? Let's go take a look. Where was that doc I was reading? Yeah, here. So it's 0 to 13. Interrupt flag register. IFR. So like right there, we see that so far anyway, in our program, we're not even touching any of the, we're not reading any of these registers. Actually, you know what I would like to do is I'd like to kind of combine these two into one table. So what I'll do is I'll do something like reads. Writes. Okay, that's better. Okay. Nope. There. All right. So no reads or writes to the T1 low order latches or T1 high order latches. But we have writes to the T2 low order latches and T2 low order counter and the T2 high order counter, 35 of them. We've got writes to the shift register, lots of writes to the auxiliary control and peripheral control register. Okay, so what the other one calls control register is really a peripheral control register. Interrupt flag and interrupt enable only got written to once, probably just during the setup. Good number of writes to the counters, to the timers here. Which is what I suspect. I actually suspect that a lot of what's going on in the Vectrex has to do with the timers. And that, you know, for example, it waits a certain amount of time showing a certain screen, and the way it does that is probably by using the timers, or perhaps I'm wrong. In fact, the timers are definitely being used for drawing. So maybe that's the thing. I read somewhere when I was looking into the Vectrex that programmers would have to like kind of get a sense for how long it took to draw things. So they would write, they would say like draw this vector from here to here, and they'd have to kind of figure out how many cycles that would take so that they could do like gameplay instructions interleaved with drawing instructions, so that they'd say, oh, you know, this should take some certain amount of cycles, that should be about 10 instructions, so I'll write 10 more here, and then invoke another draw call in order to be as optimal as possible, or at least wait before it calls another draw line, because you have to let the vector beam do its work. And I don't think they were waiting for callbacks for it to work. So I think that's what these counters are for. They're being used to do the timing of the integrators for the vector drawing. Interesting that there's 119 writes to the data direction register A. Only one to data direction B, which was that initial one we saw, but lots to data direction A. For register A. That's interesting. And yeah, reads and writes quite a bit to both output register B, to register B's and A. So they're both reading and writing there. Okay, so that just gives me a little bit of an idea of what's going on. So that was interesting. so let's go back. Kill that. Don't need this anymore. Okay, so that was some interesting information we gathered. What I would love is, do I have a document that really kind of talks about this chip within the context of the Vectrex? That could be really helpful, rather than just reading like this document is really good, but it's again more general purpose. And I will definitely be reading this to implement stuff like, here's all the information about how the counters and those timer registers work, and the timers themselves. So I'll definitely be reading that. There's lots of information here. But before I dig into that, let me just see here. I have maybe something interesting. Because I have this HTML documentation that I found. This is available online. I forget what this one's called. So some stuff about programming. Yeah, so some more technical information. It's because the thing is, it's hard to find the specifics of like how the VIA works on the Vectrex, because most people who deal with the Vectrex, like programmers and stuff, didn't really need to know that stuff. Oh, hey Slaystrom. But why a Vectrex? You mean why emulate one? Is that what your question is? Yeah. Do you know what it is? I actually own a Vectrex. It was a gift of mine from when I was a kid, and I played around with it a lot, and it was pretty cool. And I always wanted to try and write an emulator for it, because I think it's interesting having to emulate the vector display. You know, I did a NES emulator a while back, which was cool. And, you know, that's sprites and tiles and all that, which was cool in its own right and it was fun. But I thought it was kind of cool to do the Vectrex. Slaystrom says it's very expensive. Yes, it is. I guess you're looking at what it costs on eBay right now. It's about $400 or $500 in US dollars. But I have my own. At some point I'll take it out and put a camera on it and just kind of show it, although there's lots of videos about it online. It's a really cool machine. It's really got its own charm, and the fact that it's vector based means that even though it was like made in 1982, it's still kind of fun to play today. You know, vector graphics kind of look cool, right? It's like Geometry Wars type of thing, you know? I mean, obviously not as nice and not as colorful. But that's the thing with vector graphics, right? Like, they scale with time. Excuse the pun. So yeah, that's it. Like, a lot of the docs are about how to program it at the higher level. And because people would program against the BIOS routines, they wouldn't like need to know in depth, you know, how the VIA works underneath, because all of that was being handled by the BIOS itself, right? So it's abstracted away. So yeah, it's a bit more difficult to find information about specifically how the VIA is used for the Vectrex. But I'm sure somebody did it, so I'm just kind of looking through my docs here. See this internal.txt? I have it here. Yeah, you can see I was starting to read about the VIA chip here. So this device is used to control all the Vectrex peripherals. So that's actually where I copied that comment that I have in my code. The A port is used as a bus and goes directly to the DAC input and sound chip input pins D0 to D7. The DAC will output whatever value is on this port. Okay. So I guess A is used for sound. B port is used in the following ways. Ah, this is interesting. So maybe this will shed some light on those values we saw. Let me just open that up so I can compare it. Slaystrom says, the question wasn't meant to be a prod at your programming a Vectrex emulator. Just wondering if you were building as an open source program or school project, etc. Oh, no, I wasn't taking it the wrong way or anything. You were just wondering like why I'm building it? Like what's the reason behind it? It's just a fun project. It's not a school project. I haven't been in school for a little while. But yeah, no, it's just a personal project. You know, I'm a game developer by trade. I work in video games, and that's what I do at work. But at night, on my own time, I'm actually I find writing emulators really interesting. So I'm more of a systems programmer when I'm working in games, meaning that I spend a lot of my time in the lower level systems and less on the gameplay aspect. And not that I don't enjoy gameplay, I did some gameplay for a while as well and enjoyed it. But what I found was that when I do my own personal projects, I loved writing the engine for my game, you know, like putting together the engine, the editor, the tools, and all that stuff. And then when I would be like nearly done and it was time to build the game, I'd kind of lose interest and then move on. I wouldn't, like making the game itself was less exciting for me than writing the tech. And so this happened over and over. Like I'd just kind of start games and I'd write all this tech, and then after that I'd get to the point where it's time to make the game, and I'm like, I hope someone else would rather do it, would like to do it and not me. So at some point I thought, you know, why don't I try writing an emulator? And what's fun about that is that I get to write all the tech, and then when I'm done writing the tech, the games are already written, right? All the games exist and they just run on it. So it's really cool because I don't need to find someone to write games for it. And I have a working product. So yeah, I wrote that NES emulator, and then not long after I started this Vectrex emulator, and then I put it aside because I had other things to do, and then I decided to come back to it. And so that's what I've been working on for the last, I don't know, few months or something, or a couple of months, and then decided to stream it because I've watched a few other coding streams, and I think it's really interesting having people watch and share their advice and expertise, and just, you know, to kind of share what it's like to develop this kind of thing. I think can be interesting to people. So I don't know if that answers your question. Okay, let me move this to the other side here. Internal. So PB0 is the switch control. Enables, disables the analog multiplexer. See vector drawing hardware description. Okay. Slaystrom says, seems like you just like it. Yeah, it's fun. I mean, I'm not motivated by making money with this or anything, if that's what you mean. I just, yeah, it's just fun. It's interesting. And I learn a lot, right? Like I said this earlier on stream, and you weren't there, but basically, I'm not a hardware guy. Like I'm not, trained in hardware. I didn't, I did computer science, and most of my time has been about writing software, but I'm interested in hardware. And writing video games puts you pretty close to the hardware. You got to deal with performance and deal with limitations of the hardware, memory, and all that. But there's still a nice abstraction layer, and especially modern game development, you're always writing against APIs and everything's abstracted away. So emulators are cool because you can choose some old system and you get to learn the intimate details of how the hardware worked. And then you just got to kind of figure out how to emulate it, right? So it's an interesting challenge. You need to understand enough of the hardware, but not like everything. It doesn't have to be, you don't have to like really get down to the exactly how it's all wired up and all that, but just enough for you to fake how it works. So it seems to be like just the right place for me personally. Like it's the level that I want to go in terms of understanding hardware. And it's fun because, on modern computers, you can develop these things rather quickly and see results pretty quickly. So I don't have to, for example, optimize it so much, write handwritten assembly to make it super fast, because computers are so powerful today that, a straightforward implementation in C++ usually does the trick. Whereas, back in 1996, 97, when the first NES emulators came out, they were carefully written in optimized assembly and had all kinds of hacks to like make sure that it ran quickly on the computers at the time. Slaystrom says, I'm on the hardware side. I tried coding and couldn't get into it. I like watching someone write code though. Well, cool. You're always welcome to watch. Definitely appreciate it. So yeah, you're in hardware. So is that like what you do in your day job? Just thinking about how it says sample versus hold. Like if it's 0, it's enabled. The mux is enabled, otherwise the mux is disabled. So if we disable it, it's hold, otherwise sample. Okay, so we'll learn more about that, I guess, in the vector drawing hardware description. Cell 0, cell 1. Controls multiplexer channel select. Again, see section on vector drawing. Sound BC1. So chip select signal for the, so this is the sound chip, the AY38192 sound chip. BC1, chip select signal. Wonder why BC. And read write signal for the AY, so B direction. Okay. PB5 is compare. So comparator input, feedback from the op amp that does the comparison for calculation of analog joystick positions. Okay. So it's for the joystick. PB6, question marks. This line is fed to the cartridge connector. It is likely that this line was to have been used as a ROM bank select for cartridges greater than 32K. Right. Slaystrom says, I'm a student at the moment going into my last semester. I'm leaning toward server administration at the moment though. I've taken the first part of the A+, just waiting for the second part, then I will move on to server plus and security plus. Well, that sounds cool. That sounds pretty cool. Yeah. Well, keep it up. So I guess you're a fourth year then if you're doing your last semester. So the ramp. This line controls part of the vector drawing hardware. See later. It is an active low signal. The 6522 PIA has a number of control lines that are sometimes used as handshake lines as they can generate interrupts. But on the Vectrex, they are used to control the vector drawing hardware. So see, this is interesting because, you know, when I was reading about the control lines, there was a lot of information about interrupts, but here it's saying specifically on the Vectrex, they are used to control the vector drawing hardware. So it looks like we won't have to get all fancy there and just kind of focus on the specifics of how it's used on the Vectrex, which is what I want to know. So I do think this is, you know, as written here, great introduction from Keith Wilkins, though not altogether up to date anymore, a must read. Seems so. Okay. CA1. So where are we at here? What's this guy? What are we talking about? Control lines. So we're here. We're talking about this guy. The VIA control register. So CA1. Oh, there we go. So here it says CA1 IO7, which seems to be related to this SW7. So this line is connected to the IO7 line of the sound chip. Ah, okay. My guess is it is used to generate an interrupt to the CPU. See the sound description for more details. So I mean, I'm going to be ignoring sound for now and worry about implementing sound later. So that's the kind of thing that I'm not even going to care about right now. CA2. Connected to the integrators that form part of the vector drawing hardware. This line will cause them to be zeroed. This line, eh? Which one are we talking about, I wonder? Because this seems to indicate that there would be 3 bits here. I mean, maybe they're talking about the last bit here. Because it's 110. So it's probably this one. Slaystrom says, it may sound crazy, but I'm actually a freshman, but I've taken 18 plus hours a semester and I've done 3 semesters in a row. Wow. That's a lot of school, man. Is this like one of those, oh, working toward an associate's degree, 30 years young, trying to make up for, oh, okay. Yeah, that's great, man. Honestly, that's fantastic. You're not the only person who I know who's decided to go back to school, you know, after having worked or whatever and is in their 30s. I think it's awesome. So yeah, like congrats on doing that, taking that step. I know it's not easy, and you know, it's what's the word they use now? Pivoting, right? You're pivoting your career. I think it's awesome, really. You gotta chase what makes you happy, and if it doesn't matter how old you are or how young you are, it's really I totally think it's the right thing to do. You know, I know people who have gone back to school even in their 50s, and you know, to change things. It's awesome. Oh, you're welcome. So this says, connected to the integrators that form part of the vector drawing hardware, this line will cause them to be zeroed, both x and y, and has the effect of bringing the beam back to the center of the CRT. It is an active low signal. See vector hardware section for more info. Okay, that's super interesting.
Yeah!
Oh, thanks for the follow, Slaystrom. that I have to admit, that sound effect that just played kind of freaked me out. I did not expect it. That was really funny. It's like the sound effect that I put in myself for when I get a follow. It's like all quiet, and then that's great. Thank you very much. Okay, so it looks like basically, I'm guessing it's this bit here that's used to zero the X and Y position for the vector drawing hardware. So we'll read more about that later, which is just below here. CB1 not connected. Wonderful. So I don't have to worry about this at all. And CB2 blank. So here we go. Once again, looks like it would be this bit here. Slaystrom said, if I wasn't looking when it happened, I would have thought it was from Duke Nukem. No, it's a sound effect from Dungeon Master, which is an old game. It was on the Atari ST on the Amiga. And that was like the war cry sound in the game. So, yeah. And that little image that you saw was also from Dungeon Master. It's a game I really loved as a kid. It's also where my name Daru2, my alias, comes from. Well, Daru anyway, comes from that game. The 2 is because someone took the name on Twitch. And there you have it. This active low signal is the beam on-off signal to the vector drawing hardware and is used to hide the beam when it is being positioned for redraw. See vector hardware section for more info. Okay, cool. Very cool. And what I'm thinking right now is that I have all this information about, you know, what the different registers are for, and getting an idea for what the different bits are for. So soon I'd like to jump into the code here and just start, you know, writing out some bit flags and labeling and naming the registers and all that, rather than have this like array of 16. Just actually have the 16 registers and start working that way, working through defining the VIA chip this way. That's going to be a good first step, and then after that I can start implementing the logic for it. So I apologize in advance for the patronizing nature of some of the text in this section. If you know it already, ignore it. It isn't aimed at you. The text is aimed at computer literate people who may not have dabbled in the fuzzy world of digital analog interfacing. Hey, that's me. When I use the word asserted or active state with reference to a signal, I'm talking about the state in which it is active, right? i.e. ramp is only active when it's low, 0, and inactive when high. Okay. When I use the word, oh no, sorry, I just read that. It will to understand this section, it will help to understand this section if you have a copy of the vector drawing block diagram. So I think I actually have this somewhere. Let me just take a look. And what was it called? Vector.gif. Great. Vector drawing block diagram. Should try to get my hands on that because it could be useful. Nope. I wonder what he's talking about here. It would be nice to see this picture. Vector.gif. Maybe I'll do this. Vector.gif, and then I'll write Keith Williams. Wilkins, sorry. So that's the internal.txt. So I wonder if he has it in here. Nope. Oh, this is actually on GitHub. Okay. Which includes a schematic. Oh no, okay. I don't think he's referring to the schematic diagram though. No, looks like I'm not gonna find it. Oh, was it Wilkinson? No, it was Wilkins, right? Yeah. Keith Wilkins, Vectrex. Oh, already midnight. Okay, looks like I'm not gonna find this picture, unfortunately. Okay. All right, so let's see what it says. The vector drawing circuit is a mixed analog digital circuit consisting of the following parts. When the text says set or clear line or feature, refer or feature, so clear line or feature, refer back to these descriptions of how to set up the hardware for a particular function. Okay. Missing a few commas in there, but it's okay. The DAC, digital to analog converter. This is the most crucial part of the vector block. It is connected directly to port A of the 6522. Okay. See section C6522A section for details on how to set up and write to port A. So there is a section on that. The DAC takes this 8-bit digital value and converts it into an analog signal proportional to the value of the byte presented to the DAC. Digital to analog converter is port A minus offset times a constant. The range of the DAC output is from, okay, so some values lost in translation here. Be warned, there is no enable control on the DAC, so whatever value you present will be converted. The DAC output connects to the input of the multiplexer and the input of the x-axis integrator. Port A, which feeds the DAC, also connects to the sound chip. So when you write to the sound chip, make sure that either or both the blank and ramp signals are not asserted. Otherwise, you may draw crap all over the CRT. Okay. Interesting. The multiplexer, mixed digital analog. The output of the DAC is connected to the input of the multiplexer. See, it would be useful to see this picture. So the multiplexer IC, one half. The other half is used for A to D conversion of the joypad potentiometers. The multiplexer takes this input signal and switches to any one of 4 output lines. The input signal is only ever connected to one output line at any one time. The multiplexer has 3 control inputs. I think I saw that. Where was that? Is it these 3 here? The first, the enable signal, comes from the 6522A switch line from port B bit 0. Yeah, there we go. See the section 6522A section, how to set clear this bit. When this line is active, the input pin is connected to the selected output pin. Just as if a mechanical switch were thrown. When negated, the input and output pins. Slaystrom says, it seems like setting this emulator up is the same as an oscilloscope. I think you're right. I think it does have a lot of similarities. From what I read is the company GCE that made the Vectrex had a bunch of televisions, and they basically like open them up and remove the hardware that normally has it do the kind of like raster scanline stuff that it normally does in a television. And then they put in their own hardware to kind of control the vector beam using these X and Y integrators. So I assume that's similar to how oscilloscopes work. So where was I? Yeah, so the first bit, the enable signal, comes from that. When this line is active, the input pin is connected to the selected output pin. So here I guess active just means here. Enable, the bit is set to 0, so it's pulled low. Just as if a mechanical switch were thrown. When negated, the input and output pins are completely isolated from each other. Okay. The other two inputs, cell 0 and cell 1, again from port B of the 6522 bits 1 and 2 respectively. These bits are used to form a 2-bit number in the range 0 to 3. Right, so that selects the 4 outputs. And when the multiplexer is active, see above, these inputs are used to decide whether which output pin is connected to the input pin. Right. The pin channel numbers for the vector multiplexer are given below. Okay. 0 is the y-axis integrator channel. If it's 1, it's the xy axis integrator offset. If it's 2, it's the z-axis vector brightness level. And if it's 3, connected to the sound output line via divider network. Interesting. So I'm just thinking about how, you know, this is like a digital to analog converter, right? So we write a digital value and we feed that value directly to this analog, like we want it to be converted to an analog signal and sent to one of these things. So the y-axis integrator to control the movement of the beam in the y direction. The xy axis integrator offset. I'm not quite sure what that means actually. Here we're talking about offset versus channel. There's also the z-axis, which in this case they call it the z-axis. It's the brightness level. So that also is a signal we need to send to the beam. It's an intensity level, right? So how intense, I assume that controls how intense the beam will be. You know, like how powerful the beam will be exciting the phosphors on the screen. And 3, this is for sound, but I don't know what that means, the divider network. All right, x-axis integrator, y-axis integrators. Analog. So before the input to each integrator is an analog switch. So we're talking about these integrators here. This switch is connected to the ramp line from the 65 PIA port B bit 7 here. When the switch is closed, ramp 0, the integrators will integrate the value presented on the input. When ramp is negated and the switch opened, no integration action can occur, and the integrators will hold their current value. C0 function. Slayström writes, that's exactly how oscilloscopes work, at least the old ones. It's similar because it creates counter wavelengths to determine an input and output level. Oh, that's interesting. So that's where your hardware background shows. See, I know what an oscilloscope is, but I've never even used one. I have not really done any hardware, so it's really interesting. just looking at how much more there is. I think I'm just going to get through this section and I'm going to call it a night because it's already midnight for me and I'm a bit tired. But this is super interesting. So I'll be able to pick up where I'm at tomorrow because I'll be streaming tomorrow night. So should you be there, you know, feel free to join in. So, okay, so once the integrators will integrate, no integration can occur, and the integrators will hold their current value. The output will follow the following form. Okay, so that's an actual integration. Slaystrom says, I shall join in and bug you a little more. Haha, yeah, man, please. Bug me all you like. Vin minus V offset dt plus a constant. So it's a proper integration. So we've got some kind of constant here that we're multiplying by the integration of Vin minus V offset dt plus constant. So for the xy integrators, R is 10,000, and C is this constant here. And when we fill the numbers in, we get basically times Vin minus V offset times integration time plus V out start. So this magic formula will definitely be appearing in the code. Plus V out start. So that's the constant, I suppose. Yeah. Oh, so there's that offset we were talking about. Oh, I think I understand. So basically X and Y integrator channels are used to probably set the direction, how much X and how much Y we want to move in. And that basically the offset is how much to move in that direction. Slaystrom says, you can be my Linux tutor. Just kidding. If you need help with Linux, I'm not an expert, unfortunately. Mainly a Windows user, which is in large part because I'm a game developer and games are mainly developed on Windows. But I mean, I do use Linux there. I have Linux installed and or run it in a VM and stuff to make sure my stuff builds and runs on it. But it's not my main operating system. So assuming that the full deflection voltages are +5 and -5, we can calculate the beam movement. Why is my mouse all weird? Okay. This is always a relative movement based on the last position of the beam. If you want to be sure of where the beam is, make sure you zero the integrators first. Then you can be sure the beam is at 0, 0. Okay, so the -128 here refers to the fact that the screen is a 256 by 256 screen. That's not square. This I know because I took that note a while ago. Yeah, 256 by 256 non-square units. And 0, 0 is the center of the screen. So you've got the DAC value. So that's the value we input into the A register. Take that -128. Yeah. Right, it's because 0 to 256 times 10 over 256. So we're like quantizing it. And into offset similarly. The 10 over 256 comes from a 10 volt possible swing on the DAC in 256 steps. There we go. Therefore, one step is 10 over 256 volts. The -128 turns the DAC value into a plus minus value, right? Right, because we feed negative values. Slaystrom says, I can understand the offset. I've been reading on robotics while watching you. It seems to me that offset is the position that has to be reached before input will be reached. Don't let me confuse you though. Sounds interesting. And maybe right. I'll keep reading. So basically what they're saying here is like, because if 0, 0 is the center, yeah, that's it. Basically, we want to shift our values from minus 128 to 127. By subtracting 128, we shift them back basically into the 0 to 255 range, and then we take that positive value and multiply it by this. Does that make sense? Oh no, actually, because it will be interpreted as a positive value already, and it wants to make it basically a minus. Okay, it'll come in as a 0 to 255. So this will bring it into minus 128 to 127. And then the quantized voltage here to swing it. So it computes the int input and then offset that way. Okay. Seishram says, I'm not sure either, honestly. This is foreign language to me, but I'm becoming more interested. Same here, man. Delta X. So this looks like basically here. So we compute int input in offset. And then delta X is going to be minus that, this minus that. So V in, V offset, the two values we computed, times the ramp time plus X, plus the current X. Ah, okay. Because it's always moving from the very current X or Y. Yeah. So same thing for both. And then X is equal to X plus delta X. Right. So basically, what this shows is all the computation we would need to compute where X is going to be. This is really, really useful for the emulator. I'll be needing this and these to compute where X and Y should be. Assuming the Vectrex usable screen area is 8 inches, which converts to 20.3 centimeters, this is equal to 10 volts of swing. Note 8 inches is a guess. I don't have a Vectrex screen to measure, so please correct me if I'm wrong. I actually think it's 9 inches, but anyway. Also, these figures don't take into account any overdrive of the screen area and will therefore be slightly incorrect, though by how much I wouldn't like to say. So he's just basically trying to compute physically how much the beam will move on this 8-inch screen. Super interesting. How many centimeters per volt it will move. This value is again referenced to the 0 point in the center of the screen. The power supply to the integrator comes from the plus 5 volt and minus 5 volt analog power supply. No matter how long we integrate for, we can never exceed the supply rails. If we integrate for too long, then the integrator will saturate. Typically the integration time, the length of the active ramp pulse, will be quite short, in the order of microseconds or milliseconds. To move over the full range of swing, 10 volts, it will take, unfortunately no value, assuming V offset 0, V offset 0, and no saturation. Oh, I think he'll compute it here. 0.1 millisecond. This is for drawing the largest possible vector from one side of the screen to the other. So this information is actually important for me. And I mean, you know, maybe this is an approximation and I'll have to play around with it, but I do want and will need to like emulate the time, the actual time it takes for the beam to move around, because I want to emulate, yeah, Slaystrom says 9 by 11 inches. Yeah, and he's talking about X and he says 8 inches. So I think it's, you know, his values might be a little bit off, but it's a good approximation. But I think I'm going to need to take this kind of thing into account, you know, like, you know, the kind of idea of like how fast can it move, how many milliseconds does it take. If it takes 0.1 millisecond to move across the screen, I can use this to kind of estimate based on the number of cycles that have elapsed how far along my beam has moved, and then use that to kind of write values into my screen buffer, because I want to do something where I write values based on intensity, but then over time, like the values in the buffer slowly drop down at whatever rate they're supposed to drop, so that we get the whole like fading effect that we see on the Vectrex, because it's vector, right? So like if you play games in the Vectrex, you can see the fact that the lines are being overdrawn, and some are brighter, some are less bright, and some are slightly brighter on one end and on another. So that effect, to make it kind of look real and to give it, and I want to be able to give it some glow. So to do all that, I need to emulate this stuff. Like I can't be all discrete, using discrete concepts of just drawing lines and not taking into account these timing things. Although I'll probably start that way just to make sure everything works, but then eventually I want to get to that point. Okay, so I've finished that section. I think I'm going to stop here and continue tomorrow night. So Slaystrom, thanks for hanging out, and hope to see you tomorrow night. Take care.